Okay, so I think I'm recording. Let's take a look at problem 3. We need to find two things: the expression for for golf, for g composed with f of x, and then to find its domain. So the expression, well, we're going to take f and plug it into g. F is this radical, this x squared minus 9. Now, what is g going to do to this input? Well, g is going to take that input and place it underneath the radical. Then underneath that, it's going to take that input, no matter what it is, and it's going to square it. Then it's going to add 9. So what we see as the input is this radical. So what goes inside this squared is this radical, x squared minus 9. Well, we're lucky that when we square this radical goes away. A radical within a radical is referred to as a nested radical, and those problems can be ridiculously tough. Alright, so this one I get x squared minus 9 because the radical goes away, then plus 9, and the principal square root is always a positive value, so I need absolute value symbols around my x. Alright, so that's my expression for golf. Whatever you plug in, it's going to take the absolute value of it. Alright, so now let's find the domain for this. I like to think of how that function was built when I find the domain. It makes more sense to me that I always start the same way each and every time. Two things have to be true to be in the domain of a composition. First, the input has to be in the domain of the first function in order to get an output. If it's not in the domain, you won't get an output. That output becomes the input into the second function. In order to get an output of that second function, this f of x has to be in the domain of g. So we need to look and we need to find the domain of f and the domain of g. These are both quadratics here. We're going to have a little bit difficult time, but it's not impossible. To find the domain of f, I look underneath this radical, and this x squared minus 9 has to be 0 or positive. Now, I do not suggest adding 9 and then trying to take the square root of both sides. What I would do with these quadratic inequalities is factor them, and when you in factored form, I guess what I'm doing is I'm taking this inequality and I'm setting it equal to 0 because I'm finding what they call critical points. My number line, I'm going to break it up into regions. My first division, my boundary, -3 plus 3 gives me a 0, and 0 is greater than or equal to 0. +3 minus 3. So my first decision about finding the domain of f is to decide whether to include or exclude -3 and +3. Well, my answer is right here in this inequality. Since it says greater than or equal to, I can let -3 and +3 be in the domain, because when you plug them in, 0 is greater than or equal to 0. That divides my number line into 3 regions. So I can pick test points and plug them into this inequality to see whether it's a true or false statement. So, if it were me, to the left of -3, I would pick a number like -4. In between -3 and +3, I would pick a number like 0, because see, that's easy to do arithmetic on. In region C, I'm going to pick a number larger than 3. I'm going to pick a number like 4. So when I plug in -4 into this inequality, is the statement true or false that it's greater than or equal to 0? If you plug in -4 and you add 3, that's going to be negative. And if you have -4 minus 3, that's going to be negative. And a negative times a negative is positive, and a positive number is going to be greater than or equal to 0. So hey, that's a true statement. So that means I'm going to shade in over here. I'm going to shade in, if it's true for my test point, it's going to be true for all the test points from that region. Now, I'm going to erase this because I need some room. You can always rewind the tape if you need to see it again. When we plug in 0, we have, well, 0 plus 3 is 3. 0 minus 3 is -3. 3 positive 3 times -3, no way is that greater than or equal to 0. I am not going to shade, I am not going to include any point that's in that region into my domain because this is a false statement. Now, what about +4? Well, you can see the symmetry of the -4 and +4. If I have 4 plus 3, that's positive. If I have 4 minus 3, that's positive. And a positive times positive, guaranteed that you're greater than or equal to 0. I'm going to shade in because that my test point was true. Every test point would be true, and I'm going to shade that in. So now I have the domain for f. I just need to write it in interval notation. I need to describe this, tell people what it is. I can't just hand them a picture. I suppose I could, but they're not going to, I don't know if I would like that if they just handed me. I want to see it in interval notation from negative infinity all the way up to -3, including -3. And since there's a break, the mathematical symbol for being in this interval or and being in this other interval is the union. Now, remember, don't lose track of what we're trying to solve. This is not our final answer. This is just simply the domain of f. Now, it might be end up being our final answer. It depends on when we look at the domain of G, does the output being in the domain of G cause us to have any further restrictions on this domain? So let's look at the domain of G. Well, we have another quadratic inequality, but you can see kind of the symmetry, at least I hope you can see. Let's take a look at this x squared, well, wait a minute, plus 9. Boy, this is a lot easier than the last one, because over here I factored it and I found that some values on the number line produced a positive number, but some values produced a negative number. Boy, when we look at x squared plus 9, x squared is never going to be negative. The smallest x squared can ever be a 0. And 0 plus 9, this guy, for any x that you want, I don't have to have critical values. Any x at all, guaranteed that x squared plus 9 is positive. So we have, even though we have a radical, the domain for G is all real numbers, because you'll never be taking the square root of a negative number. Plug in any negative number you want for x. When you square it, it immediately becomes positive, and then it becomes even larger because you add 9 to it. So the domain for G is any real number. So there's no added restrictions to this composition. Any output of f is welcomed by G. G takes on all oncomers and says, hey, I will produce a y value for you guaranteed. You just give me any x that you'd like, any number that you'd like. I guess it's not really x, it's f of x. Any f of f, give me any number you'd like, and I'll produce an output. That's what G says to it. So the domain of my function composition, G composed with f, is this guy, is just the domain of f. It's the only restriction that we have to worry about. So my first answer was the expression itself, which is the absolute value of x, and over here, hey, that's the domain. Alright, let's take a look at part B. This time we're plugging g into the function f. G is this square root of x squared plus 9. What does f do to the input? Well, f always has a square root, and underneath that square root is always a subtraction problem. And the first number is always the input, whatever is between the parentheses, no matter how complicated or how simple it is. F is going to put it as the first number, but before it subtracts 9 from it, it's going to square it and then subtract 9. So what goes in here is this radical. But when we square that radical, the radical goes away. Not this outer radical, I'm talking about the inner one. When we square it, it goes away, and we just have x squared plus 9. Don't forget now we've got minus 9, so we have the square root of x squared, which is the absolute value of x. And that's by definition. I lost my equal sign there. Alright, let's get this over a little bit. Our first answer, we found that f composed with g of x was equal to absolute value of x. Now let's find the domain. Alright, for a composition, two things always have to be true. The input has to be in the domain of our first function. Our first function is g. This x has to be in the domain of g in order to get an output. Otherwise, it would be undefined. We would have no output. This output now becomes the input into f. So this g of x, it has to be in the domain of f, or otherwise f would produce no output. Alright, so we've got to look at this more carefully here. The domain of g, we found it already to be all real numbers. No restrictions here. The domain of f, however, was more complicated. It was this expression. This domain of f was negative infinity to negative 3 union 3 to positive infinity. So how in the world are we going to guarantee that g of x be a number either in this interval or in the other interval? Well, we're going to break it into two parts. This first interval is saying that g of x has to be less than or equal to negative 3. We have this union, or we have g of x has to be a number that's 3 or larger, that's bigger than or equal to 3. What is g of x? Well, g of x was this radical, x squared plus 9. No way, Jose, is a radical ever going to be negative. This is saying less than negative 3. There's never going to be an output of g that's in here. So that's a little bit concerning, because that's what f wants to see, is numbers that are smaller than negative 3. But f also likes numbers that are larger than 3. So let's take a look at it. X squared plus 9 greater than or equal to 3. Is that always going to be true? Well, yeah, it's always going to be true, because if we look at this, x squared, the smallest it's going to be is 0. It's never going to be, negative. So if this is 0, we've got 0 plus 9, and 0 plus 9 is 9, and the square root of 9 is 3, and 3 is bigger than or equal to 3. So we're good here. if I squared both sides, is that going to be clear? That would just be 9 and then x squared greater or equal to 0, which is always true. So even if we square this, if we square both sides, if x squared, hey, that's always true. What's the solution for this inequality? All real numbers. Any number you plug in for x, I guarantee you that if you square it, it will be either bigger than 0 or equal to 0. Okay, so that means there's no added restrictions to put over here. So even though f was picky, g magically, just amazingly, produces the right numbers. That's always in at least one of the intervals. It's always in this interval. It doesn't care. We don't care if it's never in the other interval that g likes or that f likes. G always produces a value that's bigger than or equal to 3. So f is always going to produce an output. It's always going to have a y value. Our domain for this function composition is all real numbers. Hopefully I explained it in a similar way in class. I don't remember. The domain of fog is all real numbers. Wish I had an echo effect. Numbers, numbers. Alright. Part C. G composed with itself. We're not even going to use F for this one. So that's what G composed with F is. We like to this notation, at least I think you'll find once you get used to it, makes more sense. Because what are you plugging into the function? Well, x squared plus square root of x squared plus 9. What does G always do to the input? Well, G always has a radical, and it always creates an addition problem underneath this radical. The first number it gets, whatever input it sees, the first thing it does is it squares it. Then it adds 9 to it, and then when it gets that number, it takes the square root of it. So when it squares the radical goes away, and we've got x squared plus 9 plus 9. So this G composed with G gives us an equation that is the square root of x squared plus 18. So that's my first answer for this part. Now we'd like to find the domain of this function composition. Two things always have to be true when you're finding the domain of a composition. The input has to be in the domain of the first function. X has to be an element of the domain of G. What comes out is G of X. That now becomes the input. Hey, guess what? Into G. This G of X has to be in the domain of G. Otherwise, you would not get an output. But the domain of G was all real numbers. So there's no restrictions as far as the input goes. The domain of G was all real numbers. We found that earlier. X squared plus 9 is never going to be negative. So it will always produce an output. And since you're seeing G again, its domain is all real numbers, any output is going to be acceptable input. So the domain of G composed with G is all real numbers. Because the domain of G was all, hey, the domain over here, I don't have to write that twice, do I? Domain of G, we already said, was all real numbers. So it It's not picky at all. Any number that G produces, it'll take it as input. So our first, our expression was the square root of x squared plus 18. The domain of this function composition is all real numbers. That's problem number 3. Hope that helps.